It's on page 52.
Page 53?
52.
52, thank you. I'll try to stick with the same notation. 50, yep. The complement, DeMorgan's theorem. It says A plus B complement, it's equal to A naught, B naught. Or the other one, it says A times B complement of that can be broken to A naught plus B naught. Now, boy, do I use these. On the test, on the homework, all over. Why? Well, that doesn't seem like a big deal, but when you look at this, see this one here? It says if you have an OR gate and you go ahead and you knot that, you put a knot at the end of it, that's equal to what? An AND gate with both inputs complemented. And by the way, if you take an OR gate with the knot at the end of it, we have a gate, we made a new gate. It's called what? NOR gate. So what's an OR gate? It's an OR gate with the knot at the end of it. So that's what a NOR gate is. So a NOR gate is equivalent to an AND gate with both inputs. When you see that bubble, that's the same as the knot, really. We're not going to draw a knot. That's equal to this. If you take an AND gate and you complement both inputs, that's equal to a NOR gate. And I'll give you the truth table to that in a minute. This one says if you have an AND gate with A and B going to it, then you take the result and knot that result. That's equal to an OR gate with both inputs complemented. And again, we made a new gate now, an AND with the knot, which means what? NAND. So a NAND gate will look like this. And that's equal to what? An OR gate with both inputs complemented. When you see that circle again, that's both input complemented. Now let's look at the truth table for the NOR and the NAND and show you why I use them, why I like this actually. Here's the AND gate. If this is A, B, this is A and B, and this is A and B with the knot. So this is the NAND gate, and this is the AND. When your inputs are 0 and 0, the AND gate, so the result is what? 0? Well, this is the complement of that. What's the complement of 0? 1. 0, 1. The AND gate, so the answer is what? 0. This one says 1. You're complementing the AND. 1 and 0. 0. Complemented, that's a 1. And 1 and 1 is what? This is a 1. Complement that, that's a 0. Let's look at the OR versus the NOR. A or B, that's an OR gate. A or B with the knot, that's an OR gate. if you remember, bless you, if you remember the NOR gate, or the OR gate, if you have 0, 0, what's the OR? 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. Well, this is the complement of that. This is what? 1, 0, 0, 0. First place why I like the NAND. I told you last time in the lab, we went to the lab, I don't have a single NOT gate in the lab. I never bought them. I don't have anything. So what about if I need a NOT gate? What will happen if I take this gate, a NAND gate, a 2-input NAND gate, and if I have an A coming to it, attach it to both of them. I don't know why I wrote the A twice. This is horrible. There we go. Let's see what will happen. When A is 0, right? Let me start with the 0. You have a 0 and a 0 here. What is 0? This is the NAND. What is 0? NAND 0. That'll give me what? 1. Okay. What about if it's a 1? This will be a 1 and a 1. What is 1 NAND 1? 0. So I can make a NAND gate, a NOT gate out of a NAND gate by taking both inputs, connect them together. I can do the same thing with the NOR gate. Let's watch the NOR gate. If I put a 0, that means I got a 0 here, I got a 0 here. What is 0 and 0 when you NOR it? That gives you what? 1. And when you put a 1 here, that means there's a 1, there's a 1. What's 1 NOR 1? 0. That's also equivalent to a NOT gate. Let's see. Let me take a circuit and show you why I like this method again. I'm going to build it. So let's make a function. I don't know, I'll pick one. I'll use a graph paper to line them up. Let's say I want to build a function. Here we go. I'm going to give you 3 inputs, A, B, and C. And this is my output, F. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. These are all the combinations. 0, 1, 2, 3, all the way through 7. Let me put some 1s for it. Maybe I'll put a 0, 1, 0, 1, 1, 1, 0, 0. I want to build a circuit that will generate this function. I can do Boolean algebra. We did that last time. If you remember, the minterm for this one, I want to get a 1 when A is 0, B 0, C 1. So this is what? A bar, B bar, C. I want to get a 1 here when this is what? 0, 1, 1. A bar, B, and C. I want to get a 1 here when A is 1, B is 0, C is 0. And the last one, I want to get a 1. A is 1, B is 0, and C is 1. By the way, if they don't want to give you this truth, I'm reviewing too. If they don't want to give you this truth table, we can write this problem, f equals the summation of m. M stands for minterms. Each one of these is a minterm. The function is going to have a value of 1 where?
1.
At 1, 3, 4, and 5. That's when you're going to have a 1. That's called the minterms. So a lot of times, especially on the test, the homework, I don't want to make a table like this or write this because I'll make a mistake. I'll give you the problem like this. Or I might say to you, f equals the max terms. That's the product. Max terms. M. That tells you where the function is 0. When you see that pi in capital M, that's the max term. Now, if for this function, the function is 1 at 1, 3, 4, 5. That means it's 0 where? 0, 2, 6, and 7. So I could give you the problem like this or like this. You should know the difference between them. That's where the function is 1. That's where the function is 0. These are called max terms. So if you want to find out where the function is 0, what you want to do, you want to get a 0 for the top. Well, the only way to get a 0 for the top, if you take an OR gate, not an AND, an OR gate, and do A plus B plus C. Because when you take the zeros and OR them, what's 0 or 0 or 0? 0. I want to get a 0 here. Notice what happens here. It's A plus what? B bar plus C. For the max term, we complement the ones because you want to get a 0. And for an OR gate to be a 0, the only way an OR gate will be 0 if what? If all the inputs are 0. So once you have 0, 1, 0, I get the 0, I'm complementing this, that will make it a 0, and that's a 0. And for this will be what? A bar plus B bar plus C. And this one will be what? A bar plus B bar plus C bar. So if you want to write the minterms, I'll do them both. I'll write them both. This will be written, again, minterms is known as what? Sum of products. So the ones is going to be where? A1, B1, C, A bar, B and C, A, B bar, C bar, A, B bar, C. So I might give you an expression like this or give you one like this, and it says simplify that, which means your first step is to take it from this, put it in this format so you see which one's the A, which one's the bar, which one is not. Get this expression, then simplify it.
Can you shift it over a little?
Oh. Should have shrunk it just a little bit. The max terms was going to be 0. Again, the max term is what? It's product of sums. A plus B plus C, that's the top one. Can you see it? The other one, A plus B bar plus C. The next one, A bar plus B bar plus C. And the last one is what? A bar plus B bar plus C bar. So now you have it as sum of product, you have it as product of sum. This tells you when the function is 0, the other time is going to be a 1. It does the same thing. So let me go back to this one and simplify it. Let me take the top one and simplify it, the minterm, sum of product. Let me clean it here. I want to simplify that and build the circuit. And show you where DeMorgan's theorem comes in handy. Maybe. I don't know if I need it or not yet. Let's see. I'm sure I will. Okay, look at the first two. See the first two? And look at these two. The first two you can factor out what? A bar and C. What's left? B bar plus B. Can you simplify that? That's a 1. So you end up with A bar C. Second one, I can factor what? A, B bar. That's a 1. Now again, if I was to build this, in the lab, that's A. Not that. I don't know why I put a line before that. That's a C. And it. The other one, A, B bar, and it. That's for my circuit, right? How many chips on that board you're going to need? Assuming we have a NOT gate. I don't have any, but assuming we bought one. We need a chip, one chip for the NOT, right? For the NOT gate. What else you need?
One for the ANDs.
You need one chip for the AND. We're not using everything on that chip. Has 4 of them on it. I'm only using 2, right? There's 2 empty ones. And we need what? One chip for the OR. Has 4 2-input OR gates. I'm only using 1, and 3 of them are just sitting there, wasted space. Okay. 3 chips on that board. Let's say 50 cents a piece. That's $1.50. I go, you know what? Let me put a twist on this problem, and you'll see me do that on the test. I'm going to say design this problem. This problem here, I'm going to say design using only NAND gates. Only NAND gates. Can't use NOT, can't use OR. I don't want to use them. So let's look right here. Let me look at that circuit. Let me redraw it so I can get rid of that piece of paper. This is what I have. This is A, and this is C. And this is A, this is B, this is what my design is. I said, I don't want to use AND, I want to use NAND. I said, well, NAND, that means I got to use these gates. Right? That's what a NAND gate. We can't just put a NOT there. But what about if I double complement something? What does it do? If you double complement something, does it change it? No. But by double complementing, I just made these two a NAND gate. What about this gate? Let me check my notes. What is an OR gate with both inputs complemented? That's an AND gate. See that? So that's really a NAND gate. So now my circuit looks like this. This is what? C. I go, I don't want to use a NOT gate. Make a NAND gate, convert that to be a NOT gate. Yep, that's a NOT gate. Now, I want to use a NAND, right? We said. So how many NAND gates do I need here in this example? 5. The chip has 4. I have to use 2 chips instead of 3. But if this wasn't a NOT here, I'll be in good shape. I could have used 1 chip to do all of them. I can use that NAND gate to be a NOT gate. If I need an OR gate, I can use a NAND gate in place of it if I do that. So that's really what the strength of DeMorgan's theorem is. What about if I said design using NOR gates only? Same expression. The same problem. Design using only NOR gates. Only NOR gates. Well, NOR is like OR. So I got to be thinking about what? Product of sums. Let me look at that problem. Well, I think I wrote the expression for the product of sum for it. Didn't we? This is what we have. So let me write that expression there. Product of sum for the same problem was F equals A plus B plus C, A plus B bar plus C, A bar plus B bar plus C, A bar plus B bar plus C bar. That's right here. That's where the function is 0. Let me reshuffle this around. Notice if you group the first 2 here and rewrite them a little bit nicer. I'm going to write this. These 2 group have what? A plus C in them? A plus C plus what? B. A plus C plus B bar. This is one group. The other group has, what's the same? A bar and B bar. Plus C. If you remember from last class, this is the same and these are the complement of each other. Remember what happened to them when you multiply them? You end up with this one only. And the other one, you're going to end up with what? A bar plus B bar. Again, if you design this, I say I want to use only NOR gates. This is A, this is C, that's an OR gate. This is A going through a NOT gate. This is B going through a NOT gate. All of them together. And the result is what? AND it together. That's what we have. I want to use NOR gates, so these are OR. So let me double complement both ends. Double complement here, double complement here. If I double complement, these two gates become what? NOR gates. Now I need a NOT gate, so I'll use another NOR gate to make the NOT. Now let's look at DeMorgan's theorem. It says if you have an AND gate with both inputs are complemented, an AND gate with both inputs complemented, the same as what? NOR gate. So this is also a NOR gate. So I designed this using NOR gates only. Let me try another one. By the way, while I'm talking about gates, because we brought in today the NOT and NOR gate, there's one called exclusive OR, and there's one called exclusive NOR. And probably in our book somewhere there. Like an OR gate with a slash going through it. I thought I might have seen somewhere here. Here's, by the way, DeMorgan's theorem. We're just talking about it. A NOR gate is equivalent to an AND with both inputs complemented, and the other one, a NAND gate, is an OR with both inputs complemented. I'm looking to see if that gate is mentioned yet in this chapter. Looking for a picture of it. I didn't see it yet. Oh, right here. So it must have been mentioned before. See him? That's an exclusive OR gate. And one easy way to spot, instead of searching the whole book, go to the back of the book appendix, look for the letter E, exclusive OR gates. Exclusive NOR, page 63. What'd you say, top of what page?
Top right, it says
Exclusive
exclusive.
OR, page 63 and 64. So right here. And if you look at the exclusive OR, It's this gate, and that's exclusive NOR. Exclusive OR has this symbol. And if you look at the equation for it, it says what? A naught B plus A B naught. What does that mean? If I have two inputs, and this is your F output, you will have a value of 1 when one of these guys is 1. Otherwise, you have a 0. Look at the equation. When A is 0, B is 1. Try this case. 0, 1. What's the 0 complement? 1. 1 and 1, that's an AND. What's 1 and 1? 1. So this will have a value of 1. Added to anything, still going to be 1. The other time you'll have a value of 1 when you hit that case. When A is 1 and B is 0. Complement the 0, that's a 1. What's 1 and 1? 1, and that's why you have a 1. When they're the same, you will not. You'll have a 0. Because when they're the same, this will be 1, that will be 0. Nope. This will be 0, that's a 1. Nope. When they're both 1s, this is 0, that's 1, that's still 0. This is 1, that's 0, still 0. So you have a value of 1. When 1 is 0, 1 is 1. That's what exclusive OR. And the way they write that actually mathematically, instead of writing this expression, they go A exclusive OR, like this. Exclusive NOR was the OR with the complement. Exclusive NOR. This, oh, I missed an E here. This is exclusive OR, this exclusive NOR. And you have a NOT at the end of it. So take this function, complement it. Complement of 0, that's a 1. That's a 0. That's a 0. And that's written as A plus B, oh, exclusive B with the NOT over it. That's exclusive NOR. So this will give you a value of 1 when both inputs are the same, 0 if one of them is different. This one gives you a value of 1 when the inputs are different, 0 when they're the same. This one is really equivalent to having this. So it's a complicated on the inside. That's what that gate is equal to. All of this. Equivalent. So what you're seeing two inputs A and B like this. And what they're doing, they're taking the A from here, attaching it here, and attaching it here. And they take the B and attach it here, attach it right there. So you actually, all you see is this box. You see two inputs, A and B, and that's your output F. But the inside of that looks like this. Oop. Ricardo, what are you doing there? The cover, it's all right. You can leave it. I'll take care of it. So that's what you're looking at. Just 2 inputs, 1 output, but the inside is really this whole mess. That's called exclusive OR, and this is exclusive NOR. So the exclusive NOR is just like this, except there's another NOT gate at the end of this. Or instead of using an OR here, use a NOR here. They graph them a little bit cleaner than mine because they don't want to use NOT gate here, so guess what they use? NAND or NORs. You know, they make them look a little bit nicer. A and B, complement here. So a little bit neater there. So let me take another problem I want to try. And hopefully it maybe has some DeMorgan's theorem in it. Let me take one, and maybe I can fit on one chip. Okay. Here's my question. F equals A plus B plus A bar, B bar, C bar, and D. How much time? Good. Part A. Design using only, we'll use NAND gates. Part B, design using only NOR gates. The format you in is actually what? Sum of product. That's a product. You're adding them. So this format is the sum of product format. This is going to be more challenging when we get to this part because you want to be in product of sum. So for part A, you're already in the right format. You want to be in sum of product, and that's what you have. So let's simplify it. So this is part A. Let me take the A, combine it with this one. Remember, we have one of those identities that says x plus x bar y can be written as what? X plus y. This is your y. Instead of x, I'm using a plus a bar y. I should be able to write that as a plus y. Agree with that? Now let me group these guys together. B bar. So this is my y here. B plus B bar y. I should be able to drop the B bar and write that what? A plus C bar D plus what? B. So here's the first design. I got C going through a NOT gate. The result is going to D. All of them is what? Or together with A and B. Again, if you leave it the way it is, you need a 3-input OR gate, that's one chip. You need an AND gate, there's another chip. You need a NOT gate, that's 3 chips. 3 input. If you have a 3-input OR, NAND, NOR, they come 3 on one chip, 3 of them. Each one has 3 input. Wait a minute. What will happen if I complement this, complement this, complement this, complement this? I can't complement these unless I go like this. Double complement. Single complement is not good. This is like having an equation math going, I'm going to add 5 to this equation. You can't add just 5. If you add 5, what are you going to do to the other side? Add 5 to the other side. That's the same thing. If I complement this, I got to complement that to cancel it. If I complement this, I got to complement that. So now, this is really a NAND gate, and that's a NAND gate. Using NAND. So I got these guys NAND, but these are not NAND. So what I need to do, take the C. This is a NAND gate with 3 inputs. That'll give me the C naught. I forgot what this one is.
D.
Oh, that's D. Yep. And now this is ANDed together. Was 3 input. Okay. What are we going to do with the third input? There's 3 input. Attach it to this. Attach these guys together. Not going to change anything. You can attach it to this, you can attach it to the top one. Doesn't matter which one you attach it to. Now you can take a 3 input, even if you have 2, and you make a 2 input or 3 input out of 2 almost. Now let's come back here. This is, we said what? That's also an AND gate. And the only thing of the A naught and the B naught now, so I'm designing using NAND gates. I got 1, 2, 3, 4, 5. I need 2 chips. Before 1, 2, 3, I need 3 chips. The one I'm excited about is this part. How would I get this into product of sum? That's not easy. They tell me when the function is 1. That's what this one is saying. Your function is going to have a value of 1. By the way, this is how many inputs you have? 4, right? A, B, C, D. Guess how many combinations you're going to need? 16 combinations, right? Maybe I'm not so excited about it now, after thinking about it. If you look at this, I have A, B, C, D, and this is F. If you list your combinations, 0, 1, how many times? 16. 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. The next group, 2 zeros, 2 ones, 2 zeros, 2 ones, 2 zeros, 2 ones, 2 zeros, 2 ones. Next one, 4 zeros, 4 ones, 4 zeros, 4 ones. And the last one is what? 8 zeros, and 8 ones. The reason I'm doing this because I'm trying to get the product of sum expression. This is probably the easiest way. Well, let's look at this. This function tells me when f is going to be 1. F is going to be 1 when a is what? When a is 1. Where's a is 1? The last 8. That's when a is 1. When a is 1. Also, this one says f is going to be 1 when what? When b is 1. Well, where's b is 1? These 4, right? And these 4, I already put a 1 for them, so I'm okay with those. And what else? When a is 0, b 0, c 0, d 1. That's this one. That's when your function is 1. So guess what? The rest of the time your function is going to be what? 0. That's when your function is 0. If you write that as a max term, this is what? A plus b plus c plus d. And this one is what? A plus b plus c bar plus d. And this one is what? A plus b plus c bar plus d bar, is it? That's when your function is 0. So I can write the f now as a plus b plus c plus d, a plus b plus c bar plus d. And notice these two I can simplify, right? And a plus b plus c bar plus d bar. Darn it. I can also simplify these two, right? So maybe I should write this one twice. Because if you write it twice, it allows you to simplify this one. If you just use it with this, then this one left alone. So notice I'm going to recopy this one. And now let's look at this group here. A, B, and D are the same for all of them. So you have A plus B plus D in both them, plus C, A plus B plus D plus C bar, right? And we know this one simplifies, because this is C and C bar, and this is the same. They cancel each other out. You end up with A plus B plus D. Let's look at this. A plus B plus C bar is common to both them. Plus, is it D bar here? A plus B plus C bar plus D. And D and D bar will cancel each other out. You end up with A plus B plus what? C bar. Can I simplify any more? Doesn't look like it, huh? So here we go. The design, A, B, D, OR gate. A, B, C going through a knot. Another OR gate. And the result is what? And it together. For this, we wanted to use NOR. Was it NOR? Is that what the question was? What did I say? Use NOR only, right? Using only NOR gate. So let me double complement these. It's the same circuit. So if I do that, I have A, B, and D. NOR A, B, here's the C. I gotta take this, feed it through another NOR gate to make a NOT gate out of it, attach all three legs together. NOR gate, and that result is NOR together. Well, if this NOR gate has three inputs, just like the rest of them, then I'll take one of these, attach them twice. Doesn't matter which one. That's if you build this or you build the previous one, your answer is not going to change. This will tell when the function is 0, which is right here. Any other combination of these, you're going to have a 1 here. So this is the same as the previous one. It's the same as this one. They give you the same function. Except it looks like I'm using less gates here than this one. But the number of chip probably not going to change because 1, 2, 3, 4. They only come 3 on a chip that has 3 inputs. So 1, 2, 3, 4, 5 here. Less connection. Again, just time-wise, we'll reduce the time of building this circuit. Okay. So this is how we use DeMorgan's theorem.